Yeah, good morning. So, yesterday what we have seen was introduction to parallel computing and how we can use parallel computing. What is the need of uh, using parallel computing? Yes, and mainly we have seen OpenMP or shared memory uh, parallelism, where shared memory parallelism and limitations of that. So there in shared memory, it is we use multiple cores in a given CPU, and there is limitation on how many cores we can have in a given CPU. So one need to rely on more hybrid kind of thing, and in that case, distributed computing comes into picture. In case of distributed computing, what we have is we have multiple nodes which are connected together using some high throughput network, and data is divided across multiple nodes, and we perform several operations, or we just perform some computations on individual uh, nodes, and once we perform operations, whatever intermediate results are there, that or final results, we can transfer it between multiple threads or multiple MBA processes. uh, Also we have seen point-to-point communication, where we can transfer data between two processes using MPI send and MPI receive. Those are the blocking calls, means once we execute the send command or send command is executed, it will wait for corresponding receive receive statement. Unless and until the receive statement is completed, send call will not complete. So after point-to-point communication, what we have is collective communication. Means in case of collective communication, what we do is as unlike in point-to-point communication, two processes or two MPI processes communicate with each other. Here, single process can communicate with rest of the processes. Means if you have five processes and you want to send some data to all the processes, one can rely on collective communication. The collective communications can be divided into three parts. First is synchronization, means you have n number of processes and you don't want to execute the next part unless and until it reaches to certain point in your code. If you are, let's say, computing some values, and once those values are computed, then only you want to perform the next stage. So you can use barrier for that. So all processes will wait till they reach the barrier statement. Once barrier is executed, the execution for all the processes will start. So, yeah. Here you can see I have rank 0, rank 1, rank 2, and rank 3. So rank 0 has uh, have done a few things, and then rank 1 has more things to compute, and there is a barrier statement. So all these processes will wait till they reach rank 3, reach to barrier stage, and once rank 3 reaches to the barrier stage, then all the processes will again start their execution. Secondly, there is something called as data movement. So if you want to transfer data among all the available processes, the data movement collective communication can be used. It contains broadcast, scatter, and gather. Now, broadcast means you want to send or share some data among all the available processes. So one can rely on broadcast. So here I have one process and which want to share some data among all the available processes. So broadcast can be used. It takes a buffer. The count means how many elements you want to send. The data type, who is the root of the broadcast, means who is broadcasting the data, and your communication word. Next, let's say you have series of data, or just for simplicity consider an array. Now you want to divide that array among all the available processes. Let's say you have 20 elements and 4 processes, and you want to divide the available data or those elements among the available processes. One can use scatter. So what scatter will do is scatter will evenly or uniformly divide all their elements to available process. Now you can see I have used the color code for the scatter. Means let's consider this as an array, and here for process. When I perform scatter, this data has been distributed. Means red part is given to one process, yellow is given to another, green is given to another, blue is given to another one. So that way scatter will distribute the data across available processes. Now you have performed the scatter, you have performed some computation, and you want to collect some results. So one can rely on the gather. So gather is exactly opposite of scatter. What it will do is it will collect the results or some data which is available across all the processes to a single process. So it needs buffer which you want to send, the total number of elements you want to send, the data type, buffer on the receive process, how many elements you are planning to receive, what is the data type which you are planning to receive, who is the root who will be accepting this data in your communication. And finally, we have reduce. We have seen reduce in OpenMP. Reduce, what reduce does is it collects the data on a single process like root, whatever root you give. So it will collect the data on that root process. Along with that, it allows us to perform some operation on that data. So if I perform reduction of this number using addition operation, so what it will do is it will add up all those values, and then whatever result is generated or whatever result of summation or addition is there, it will be assigned to your reduce root. Means if you're performing reduce on rank 0, it will uh, save the addition to rank 0. Yeah. So we can now see some examples. Okay. Yeah. So yesterday we have seen this hello program where we perform initialization, get communication size or the total size of your environment. Then we get rank of individual process and processor name. So in case of broadcast, what we are doing is initially we are getting initializing the MPI environment. Once MPI environment is registered, we are getting rank of individual process and the size of communication world, and we are checking whether we have rank 0, and we have barrier statement over here. Means it will not perform broadcast unless and until some input from command line is accepted. Now this accepted input lies with only rank 0. It is not available with other rank. So what we are doing is we are performing broadcast, and we are sending n or broadcasting n. Size is 1 because it is a single element. If it is an array, we'll change the size accordingly. The size of or the data type of that element is integer, so we are saying integer MPI int. This value is available with rank 0, so rank 0 is the root, and we want to send it to all processes in MPI world, communication world. And then we are just printing the rank and the broadcasted value, and we are clearing the MPI environment. Now let's try to run it. Now how do I run this MPI code? I can use MPI run -MP, the total number of processes which you want to run, let's say 4, and the executable. Now it will ask me value of n, and all the processes will wait till we enter some value because we have given the barrier statement. Let's say I enter 10. So the 10 value will be broadcasted to all available processors. Yeah. Next is scatter and gather. So in this case, what I'm doing here is I have defined an array of called as data of size n, and n is defined set to 10. And I'm initializing the MP environment and getting the rank and size. And at rank 0, I'm initializing that data with index number, just 1 to n number of elements. And I'm calculating sub n, which is the total number of elements which should be processed by individual processor. So this sub n lies with rank 0. So first what I'm doing is I'm broadcasting value of sub n. So sub n will be available with all the processes, and then I'm scattering the data. So if I have 10 elements and I scatter it in 5 processes, so each should get 2 elements. So this is the data which I want to scatter. Sub in is the size which I want to assign it to individual processes. Data type of the array which I want to share. This is the location, memory location where I want to accept it. So total number of elements which I'm expecting. The data type. Who is scattering the data? Rank 0 and communication word. And finally, at each rank, what I'm doing is I'm just printing the results and modifying the data. Yes, I'm scaling it up 10 times and performing a gather. So performing gather, and I'm planning or I'm collecting all the updated values at rank 0. Again performing a barrier. So once gather is complete, then only it should go and complete the go to the next statement and printing the results, because I have collected the or I performed gather with root is equal to 0. So all the gathered data lies with only rank 0. So I'm checking if it is rank 0, then only print the modified data. So whatever data I have assigned, it should be multiplied with 10. And finally, I'm clearing the MPA environment. Now let's so as I perform scatter, you can see up to here, I have 10 elements which are divided across the available processes. One can do it manually as well, but scatter will help us to divide that data automatically. So it calculates what data should be given to which rank, and accordingly it gives. And then we have scaled the data, and the scaled data is received at this rank 0. So 10, 20, 30, 40, 50, 60, 70. So yeah, we have got the or we have collected the results at rank 0. And then what I've done is yesterday we have seen uh, some routine to or OpenMP code to compute value of pi using shared memory operations. So here I am demonstrating the similar thing where we are trying to simulate these many photons, and I divided the date n with the available processes. Means if you have 100, then 4 processes, each process is responsible to calculate or generate 25 random numbers. Then I'm calculating start and end and generating a set of random numbers and checking whether that random number lies inside the circle or not. If it is lies inside the circle, I am incrementing some temporary count. And once that is done, I'm performing the sum operation on that counter and just normalizing it with the total. This is stored in variable called as insight, and just normalizing with the total number of simulated photons and scaling it up. And let's try to run it. Yeah, you can see the simulated value of pi, and the we can just check the execution time, so we can compare it with other. It took somewhere close to 7 seconds. Now we'll compare that with CUDA. Yeah, this was about OpenMP. You have any questions related to this? If not, we can go ahead with GPU computing. So in our CPU, what we have is a few arithmetic and logical unit, one control unit, one cache, and one DRAM. So this is the standard architecture of our CPU. And in case of GPU, instead of limited arithmetic and ALUs, arithmetic and logical unit, we have many more ALUs, and each set of ALU has a control unit and a cache associated with it and a common DRAM. Now, whenever we perform some operations, these ALUs will share their control line, and whatever instructions are passed to ALUs, those will be executed simultaneously. So eventually, in GPUs, we have several thousands of transistors, and those each transistor will act as an arithmetic and logical unit. Now, how does the CUDA or GPU computing work? In CUDA, the memory is divided into two parts, or basically we call it as a host memory and GPU memory. Host memory is the memory of your CPU, and GPU memory or device memory is the memory of GPU. So initially, the flow of CUDA processing is as follows. Initially, we will have all of our data in the main memory. We can read it through some file, or we can generate it, or we can initialize it. And that data is not available with GPUs. So CPU instructs the processing, and then uh, that data will be transferred from CPU to GPU. That is the first step. Once data is transferred, then CPU will instruct to GPU to perform some operations. Once that instruction is given, GPU will start processing the supplied data. Once the processing is complete, the results or whatever results are generated, those results lies with GPU memory only. So again, we do not have our main memory or CPU memory doesn't have access to GPU memory. So one need to transfer data from GPU memory to CPU memory again. So that is the final step. So first, get your data in main memory, transfer it to GPU memory, perform the operations or computation you want to perform. Once operations are performed, whatever results are generated, copy back to GPU and then perform the post processing. So this is the CUDA processing flow. Now, in case of CUDA, the functions are divided into four types. Host functions. Host functions are the functions uh, which will be executed on the host or our CPU. Then global functions. Now, when we define a function on a GPU, we need some interface to call that function from the host or CPU. So global function allows us to achieve that, and it is nothing but it is just an interface between host and device. Means you can call global functions from a host, but it will be executed on the device. Now these two memories are completely different. Means in case we are calling this from host, and the actual computations will be performed on the device. So global function doesn't return any value, so its return type is always void. Now we have something called as device functions. Now device functions are the functions which will be executed on the device, and you can specify the host function just by giving underscore underscore host before the function, global by giving underscore underscore global underscore underscore. I'll show those things. And device, you are using underscore underscore device underscore underscore. So device functions will be executed on the device, and they can be called from the global function or from other device function. One cannot call device functions from the host functions. So just we'll go through our first CUDA program. So what we have over here is I just included st.h for printf thing, and we have kernel, which is a global function, and we are specifying one thread with one block. I'll tell you what is the threads and block, and we are just printing hello world, and this is my global function. I specified it kernel as a global function by giving underscore underscore global flag before the function name, and it accepts it data type of or the return value of the kernel, which is a global function, is void, and it is not accepting any values. So how do I now compile the CUDA program? One can use nvcc file name. In case of CUDA, the extension is .cu, and some object file where you want to transfer your or generate your result or compile your code. And you can just execute it by using /hello. Now, if I want to check or see the properties of my CUDA device, one can query the GPU card, and that can be done using device query. So in CUDA, there is a structure called CUDA device properties. One can generate an instance of that structure and initialize all these values and check basically what is the type of the GPU card, how many threads are available per block, or how many threads dimensions are available, what is the clock rate of your device. All those information can be easily available. We will execute these things in some time. Now I will talk about thread. Uh, Thread is nothing but a single process or which will execute the instance of the kernel or device function. A set of threads are called as block. Now here you can see we have a block which has n number of threads, and this set of threads is called as block. Now several such blocks form a grid. In our device we will have several grids, or in principle we can have several grids, several blocks, and several threads per a given block, and one can synchronize threads in the block, but it is not possible to synchronize several blocks. These blocks can run concurrently. And in GPU we have several memory types. First is register. The register memory is only specific to a thread. Is whatever data is stored in a register memory is visible to the thread who wrote the data. Secondly, we have shared memory. The shared memory, the data stored in the shared memory is visible to all the threads in a given block. The threads in another block cannot access the shared memory. Means if you want to share something within a block, one can rely on the shared memory. Then we have something called as constant memory. Let's say you have some data uh, which you are expecting not to change over the your kernel execution. So you can use constant memory and store that data in the constant memory. And finally, your local memory, it is something similar to uh, register memory, but it is slightly slower as compared to your register memory. And the last is the global memory. The data stored in the global memory is visible to all the threads within your code block. So in case of shared memory, the data is visible only to the threads which are part of that particular block. But in case of global memory, the data is visible to all the processes or all the threads in the application. It is the slowest memory, by the way. So the fastest is register memory, and global memory is the slowest memory. So uh, you can allocate the CUDA memory using CUDA malloc function, and one can copy the results using CUDA memcpy. So it needs destination, source, the size, and there are several enums which defines the type of the operation, means whether you want to copy the data from host to device or device to host. So, or device to device, one can perform the or mention the type of the operation one want to perform. And finally, when if you want to free release the memory, one can use CUDA free. We will see some uh, examples. Okay, I will answer this question towards the end. So first we'll compile the hello world, and I'll simply say now the code for that is here. Yeah, it's the same thing which I showed earlier. We have something called as global, and we have kernel, which is the name of the function. It doesn't accept anything, and we have void data type, and we are calling one block and one thread per block. Now, what if I just say, okay, I don't want to do the global? What will happen in that case? Compiler will throw an error saying host functions cannot be used to call the device functions. It should be global only. Yeah, I talked about the device properties. Uh, Initially, what one can do is one can use CUDA get device count function. It will give us the available CUDA devices, and then iterate through all the devices. And we have this CUDA device property structure. I created an instance of that and called a function called as CUDA get device properties with reference to the structure and your device count. If you have three devices, you can their indexes will be 0, 1, 2. One can pass that particular index our information uh, about which card you need. You can pass that index to get the information or properties of that particular device, and then I'm just printing the properties of the device. So here I just listed these properties. I can compile and hmm, now you can see here we have only one CUDA device. This is the major number, it is the minor number. The name of the GPU card. We have Tesla P100 16 GB GPU card, which is connected over the PCI Express card or PCI bus. It has this much global memory, this much shared memory. It can have 65,000 registers per block. The dimension of the block, we can create multi-dimensional block, this one dimensional, two dimensional, three dimensional, up to it support up to three dimensional. So each dimension can be of 1024 size. And then the clock rate of the GPU card, the total constant memory which is available. Constant memory is used to store the constant variables, and whether, yeah, how many multiprocessors it can execute at a given time. All this information can be uh, one can get that information just by using this CUDA device or CUDA device properties function. So what I will do next is, okay, before going to that, I would like to demonstrate the another thing. So I've shown us here a simple example. If you want to perform addition of n numbers, so what one can do is just allocate the CUDA memory, call the kernel, and perform the actual operation inside the kernel. So for that, we need to, once the operations are performed, we need to copy back the results from device memory to host memory and finally print the results and release the memory. And if you have a large array, how shall I perform the index mapping? Yes. So let what we have is thread ID. It is nothing but the ID, unique ID associated with digital thread, and it can have multiple dimensions. So for simplicity, I have considered one-dimensional uh, threads in one dimensions. We have block ID, ID associated with integer block, and then we can get the dimension of the block. Now one can simply get the TID, or basically the index of the element with specific block, by using thread idx dot x plus block idx. It should be into, not plus, star block dimensions, means your block ID multiplied by dimension of your block plus thread ID. So let's say I want to get the index for thread ID 5, block ID 2, and here the size dimensions of my block is 8. So eventually it is the 21st element in my block. This allows us to divide our data across the available threads. So if you have multiple dimensions, then accordingly you can change your thread x and thread y to get the indices for your particular array. Now, if you want to check the error, means if you have performed some computations and you want to check whether there was some error during the execution or not, one can use CUDA get last error function, and if there was some error during your previous command execution or statement execution, it will give you that particular error. Then using this CUDA error T, it is a structure. One can get the name of the error and the error message. You have to supply that to get CUDA error name and CUDA error string. And in order to get the timing, one can create the events. So basically, what you can do is you can start the timer, perform. Basically, you can create instances of start and stop, which is CUDA event. Once that is created, you can start recording the time, perform some computations, other computations one need to perform, and the finally get the difference or execution time between two events by using CUDA event elapsed time. So it will give you time in your floating variable, whatever you have defined, and it will accept the instance of CUDA event T structure, and it will return the time in millisecond. So let's try to see some more function. Okay, last slide. Then you can go with the some of the demonstration. So what are the limitations of CUDA? So CUDA doesn't support recursive function. Means recursive functions are like function calling themselves. So if you have some function which is calling to itself, it is difficult to use those kind of or report those kind of functions in CUDA. Uh, Due to memory limitations, it is slightly difficult to use 64-bit floating operations, and there are many deviations uh, from floating point standards. It doesn't provide us texture rendering. Sometimes the latency between the burst and of the CPU and GPU can be bottleneck. It is always recommended to run in case of CUDA, it is always recommended to run threads in group of 32 means if you want, because there is something called as wrap which shares the set of instruction which is of size 32. So hence to achieve the best performance, it is recommended to run the threads in the set of 32. Means you can have total number of threads as 32, 64, 128, 512, or 1024. But if you use some odd numbers like let's say 100, 200, it is not always recommended due to the performance. And CUDA supports only NVIDIA GPUs. One more thing, so CUDA is mainly useful or gives the best performance if you have something like single instruction on multiple data. Means you have some data set and or some data where you want to perform similar instructions on different set of data or different data sets. One can go with CUDA, but if you are planning to perform different instructions on the different data set, CUDA is not uh, recommended for that, and you may not get the best performance in that case. And again, if you have multiple if statements uh, in your code, that also can affect your performance. Now we will go and see some of the remaining examples. Let me close this first. Yes, this very. So, okay. The first thing is just to add two integer numbers, and I imported studio.h, then declared two variables. One is the variable on the host, which is called as sum, and another is variable on the device. And allocated memory for the variable on the device using CUDA malloc. I have uh, given it is a double pointer of type void, and allocated size is for single integer elements. Then I have called the global function, which is defined over here and will be executed on the device with one block and one thread per block, and pass two elements 1 and 10, and the result is received in the variable sum underscore device, which if, for which we have passed the reference in the global function. And this result is again on the device. So I perform CUDA mem copy to copy the results from device to host of, and the size of the result is just single integer element, and printed the result and release the memory. Let's see. Yeah. So you can see the addition is 11. So the computations were performed on the GPU. Then uh, just to demonstrate the memory mapping, I've given an example of dot product. So here I've declared a few arrays and a temporary variable for dot product, and then it's this. So those arrays or two vectors are initialized on the host. I just given the same values to both the arrays, and those were copied to the device because these are declared on the host. I copied them to device using CUDA mem copy, given the location on the device, or this is nothing but destination. Source, I want to copy the results from host memory. The size, how many elements I'm planning to transfer, and the operation. So in this case, I'm planning to perform uh, or copy the results or the data from host to device. Then computed the total number of. So here I have hard coded or I have decided the total number of threads per block will be 256, and I know my total number of elements which are declared earlier. Using that, I've calculated the number of blocks, which are nothing but total number of elements I want to process divided by threads per block. This will give us the total number of blocks. Then call the kernel dot product with number of blocks, thread per block, and pass the variables which were declared on the or device, and pass another array to store the results. So what this will do is this will give us the partial results. It will perform the multiplication on the device, and it will give us the temporary array to us. So here, as mentioned earlier, what I've done is I've computed the IDs or indices by using thread IDX plus block IDX multiplied by block dimension. It is nothing but just simple index mapping, and I'm just checking whether my TID is less than n or not, because we have uh, while calculating the blocks we have said +1. So I'm just ensuring just to avoid the memory leaks, I'm saying this TID should be less than n, and computing or performing the multiplication. The elements at A and B will be multiplied and stored in the temporary array called C. And once that operation is performed, I'm copying back the results from device to host and perform addition of the intermediate result to get the dot product and just printing the results. So now let's try to execute this. Sorry. Yeah. So this is the dot product. I gain some large number. So this is the dot product of the array which occurred, and execution time is almost 0. And finally, going back to the similar example where we have computed the value of pi. So in using MPI, we have seen that the execution time was somewhere close to 7 seconds. And here also, in this case, I have hard coded the total number of blocks and threads per block because I know the total number of elements which needs to be simulated. And calculating 7, which is again yeah, sub part which each thread will execute, and calculating that, allocating memory for pi on the device and the state of the device, and performing the compute pi operation, or calling the compute pi kernel with pi device and device state. Device states are used for generating the random number. Now here I have calculated, or basically computed the index of each for each array element or for each thread by using similar thing where I use thread ID, block dimension, and block ID, and some variable which are used to define whether it lies inside or not, and initialize the CUDA random generation function. So given some C thread ID and the states, and generated the uh, uniform random number, or a set of uniform random number x and y with the states, and check whether it lies inside the circle or not. So if it is lies inside the circle, I have implemented the, and here only for each kernel or each thread, I have computed the estimate of pi for that particular thread. Now, if you have, let's say, 512 threads in a given block, you will have 512 estimates for the value of pi. Now, these estimates are copied back to the host memory, and see. So I have pi host, pi device, and this is the total number of elements which I am planning to copy back, because we have a number of blocks into number of threads per block, and then we have these are floating elements. So these many estimates we have, and then I'm specifying this. We should copy the results from device to host. Once we get the uh, results, what I'm doing is I'm averaging them out. Means initially uh, getting combining, summing all the estimates which we have generated, and then normalizing them with total number of blocks, and basically total number of threads which we use for the computation and stopping the timer. Printing, and finally I'm printing value of pi, and then computing the error. So now you can see the execution time is 0.12 second, and in case of MPI, sorry, I need to put time. Here I'm not having time. Yeah. It is somewhere close to 7 seconds, and using CUDA we managed to do the similar thing in only 0.12 seconds. You can see the performance gain just by moving from MPI to CUDA. And if we go with single-threaded application, so let me just say run it with thread one. It will be much more than that. It may take quite a lot of time. Yeah, meanwhile, yes, I can. If you have any questions, you can ask. Yeah, so it's 25 seconds with single-threaded application, and using GPU, we managed to do it only within 0.12 seconds. Yeah, that's it from my end. So then you can ask if you have any questions. Okay, there is one question from Slok Shah. Uh, how does one grid represent one core? Uh, Grid doesn't represent a core. Means grid is nothing but a collection or a group of threads which are basically what we have is a set of blocks which has set of threads, and set of blocks are again form a grid. So it doesn't represent a core. We have something called SMs, and those SMs will execute individual grids on them. And depending on the GPU card, the total number of SMs will change. There is multi-threading available in there is another question by Amit. You never refer to multi-threading in Java. Yeah, but there is multi-threading available in Java, but it is not that efficient as compared to multi-threading available in uh, plain C. And again, it is a shared memory operation. Means you cannot use it across the multiple nodes. If you want to do that, your means the multi-threading available in the Java is only limited to a single CPU. Java, I think, does support OpenMP. I'm not very sure, but it does. Yeah. So the main reason for going with C or C++ is due to the distributed computing. Is there any other question? If not, then I think I'm done with my talk. You can stop here.